Hello, everyone. This is lecture 24 of PTRE 465531, Petroleum Reservoir Geomechanics. The last lecture was a very important lecture because we learned how to deal with drawing the polygon, which is very important tool to have in your arsenal, especially if you are doing research related to this stuff. I think if you can, where is it? If you can draw the polygon and it has a lot of utility. Like you can use it for a lot of stuff. So whatever you can do on the more Coulomb, more circle diagram, you can really do it in the stress polygon. And it looks smart. Now we have only used more Coulomb, more circle, and stress polygon for shear failure, but we are gonna see next class in the well completions how you can use the stress polygon for tensile failure. And we don't really show the more circles showing indicating tensile failure, but you can do that too. It will be on the negative values of on the negative side of the more circle. But yeah, we did basically say you take the polygon. Polygon is a Greek word, means multiple sides. Multiple angles actually. Gonia means angle. So basically you have the dotted diagonal is y equals x. Anything below that is impossible by definition, because SH max must be bigger or equal to SH min. Then you have this small vertical line, this line, which is basically from the normal faulting side, SH min over SV, a fixed value, 0.62, I think, or 56. Then you draw the horizontal line, which is for reverse faulting. You plug in S1 as SH max, S3 equals SV. SV is constant 1 psi per foot. PP is also a constant 0.433 SV. And then everything else boils down to SH max equals 2.2017. And then the third line is kind of harder, but it's going to be in the form of y equals mx plus c or ax plus b. And you have two variables now, and you draw it. I think you guys would be, it's not that hard to draw. It's like, what, 4 lines, including the diagonal. Not terrible. And then, okay, you add the coloring of our very smart friend, Dr. Lundstern, and you basically include the Simpson's alpha p magnitude, basically. The higher the magnitude, the closer you are to reverse faulting. The lower the magnitude, the closer you are to normal. Okay, so that's the extremes. And example problem number 2 that we saw a little bit fast. It's a very important example. And you're going to have something very similar for your homework 3, which is basically how do you call it, a saltwater disposal problem. I'm injecting water, I'm increasing the pore pressure in the vicinity of the well, then suddenly I get faults in that vicinity slipping. And these are basically fault reactivation or slippage along pre-existing faults. Once this pile up, they become bigger and bigger in magnitude. Eventually, after a magnitude of 3, you start feeling them as earthquakes. And it goes on like this. The effect of that, to show it pictorially or graphically on a stress diagram, on a stress polygon, basically, you have the point of the stress state of the Fort Worth Basin that is fixed for our considerations. In real life, it's not fixed. It's moving a little bit up it's moving like a little bit in the direction parallel to parallel to the diagonal. So it would be moving like this a little bit during the pressurization, and like this during depletion. In this case, pressurization, but we assume it stays the same place. So the first polygon before I start injecting is the purple one. My dot is very much within the purple polygon, right? So I'm safe. Everything is fine. But as I inject, I end up getting here. The polygon shrinks.
Now it's increasing PP.
Yeah, increasing PP, exactly. So as Malek said, you increase PP, you lower, make the polygon smaller. Eventually, it just touches your point. That's the critical value. After that, you start having earthquakes. Yeah, and it goes on like this. With the now the relationship to Mohr circle is something that I think you guys already understood. Basically, if I'm outside of the polygon, I have failure. And obviously, I can adjust the polygon for poroelasticity. You're gonna see that in the homework too. Depending on the poroelasticity, the smaller the value, we said alpha B varies from 0.6 to 1, roughly speaking, but there are people who say for shells it can go as low as 0.3 or 0.2 even. It's very hard to measure alpha B in the lab. Very, very hard. With confidence to measure it directly. Very, very hard.
Alpha B is
Biot's poroelastic coefficient.
yeah, bios.
Yeah, it's basically the smaller that value is.
You can calculate it.
Yeah, but you cannot like measure it experimentally very easily. You can, there are ways, but it's
The auto does the biot coefficient.
yeah, but it's not very easy to
it's not,
constrain it that much. I know when you have clays, it gets low. Because clays, it's like gumbo, it's like mushy, it goes off. What did we say about BOs? Is the ratio between undrained and drained, something like that. And we said, what did we say about it?
It doesn't go more than 1.
Yeah, it cannot go more than 1. And
0.7 is a lot.
It's pretty low. But I mean, I heard McClure saying in a presentation that they measured some shales in the Stanford and they found as low as 0.3. Yeah, this is crazy.
For stones, they used to take 0.6.
Sandstone though doesn't have a lot of clays, right?
No, like
almost no clay. Yeah. Oh yeah. Yeah, those values make sense. So the higher the value of alpha B, the smaller the polygon becomes. Okay, so low alpha B values make the polygon bigger, from my understanding.
Is the friction.
Yeah. Well, Nassim has a paper from last ARMA. You can find it in one Petro. He has a lot of polygons, and he shows the effect of everything on the polygon, like a different polygon. I think he has the different lines to show like as alpha B decreases. Where is? Let me see if we can access it very quickly because he shows it pictorially. One Petro. Yeah, I think it's somewhere. Where is it? Okay, this is the impact of new. So you go from small mu is the dotted line, then the solid line is 0.6, and then 0.7 is the dashed dotted line. So mu increases. If mu increases, the polygon increases. Okay. Don't worry about the colors, but no, he doesn't have a polygon changing with on the poroelastic effects. He only has the lines changing. Yeah, but
Induce the fracture, huh?
yeah, he doesn't have the here he doesn't have the polygon changing. He should have, actually. But here he has the pore pressure effect, which is basically okay, pore pressure goes up, the polygon goes smaller, right? So it looks very bad on the projector. On the screen it shows correctly, but this is blue, not black. It's too black for yeah, hey Nassim, how are you? What's wrong?
Hakim, nothing seen. That's Hakim.
Yeah, did I say Nassim?
Yeah.
Oh, yeah. Anyway, I was late today. You will understand why. In the next slide, actually. Anyway, so where were we?
Are you recording?
Yeah, it's recording. Why?
Because I don't see the blue.
Something changed.
Something wrong with the color.
Yeah, something changed in the class because this clock says 7:50. It's 2:50. This stuff, they were not looking down last time.
No.
Something changed.
When you check the Zoom, you are sharing the screen.
Yeah, I'm sharing the screen and I'm recording. Yeah.
Because the screen, I just should be in.
Yeah, I don't know what it happened.
Is anybody online?
No, just us. I know if it's dark blue, it shows as black, but it shows correctly on my screen. Anyway, so today we are gonna see another plot that is maybe doesn't have the utility of the polygon, at least not yet. We are actually working on finding some utility real time, literally. So we were talking about it like an hour ago, 2 hours ago. And there would be, it's good to know how to draw it, okay? So it's from Lundstern and Zoback, 2022. That's what they used to cite it, actually. This plot shows the limits of SH max and SH min to shear failure, honoring the Moore-Coulomb failure criterion, of course. And similar to the polygon, it shows all the stress states that are possible, right? From 0, alpha p 0 on the x-axis to alpha p equals 3. Very, very normal faulting on 0, very, very reverse faulting in the, by the 3. And what about the y-axis? We have stress, and to make the numbers easy, instead of having thousands, I'm having it normalized by SV. Or he has it normalized by SV. And then I made this plot, but it's Lundstern sort of idea, this plot. So, okay, let's see how to draw it, because it might be a little bit more complex than the polygon, but it would be, it's doable. Huh?
Those are those slides?
What's
You
those?
were working on the slides?
Yeah. I literally finished them 2:18. And then I went to the restroom. And then I got out, it was 2:29. And I had to come over. And that's why you didn't find anybody in the class. Anyway, every plot, just like the polygon, is for a fixed a fixed pore pressure. And if you want to include pore elasticity, he did not include pore elasticity. It's very easy to include if you want alpha B. Okay. Then you have two straight lines that you see, the black and the dotted, the black solid and the dotted, just the dots basically. Let me, because the people online won't be able to understand what I'm talking about. It's SV and whatever. This is SV. And then I was talking about this one for pressure. Obviously, SV must be bigger than, at least equal to pore pressure. It won't be, it cannot be smaller. None of the stresses can be smaller. Now, if you see the vertical lines, you have two dotted sort of lines here, here, and here. They separate the three regimes. Okay, you have, let's see, normal faulting, strike slip faulting, reverse faulting. And I'm talking about these lines. They separate. So we really have three regions, right? Three regions. The left region, the right region, and the middle region. So now we want to draw two lines on each region, right? So I want to draw the limiting magnitude of SH mean with a dotted line, dotted black line, dotted thick black line, and the magnitude, limiting magnitude of SH max with the dashed dotted black, thick black line. Okay, so I have to draw 6 lines. Okay, 6 lines. And they are indicating the limits to shear failure. So I have to draw 6 lines, but I'm going to make it out of 2 equations. One is the equation that you guys know very well now, and I told you the exam, most likely, every long question of the second exam will only involve this equation. So if you know this equation backwards and forwards in terms of how to use it, you don't have to memorize it, it would be there. You would be good. And then another equation, which is basically from module 1, this equation. So I have 2 equations, and I need to come up with 6 lines, okay? So what is the easiest to start with is the limiting magnitude of SH mean and normal faulting. Okay, so I want to draw first this line. Okay, I want to draw this line. If you notice very well, it's a constant value, right? Okay, that means it's easy to draw this line. And it's very easy to draw this line because this line is basically this line. Okay, that's the 0.52 or 62 or 56, whatever it is. So I'm basically, how did I draw this line? I took this equation and I make this as V, which we said is 1, right? And then I make this the SH mean value. Huh? No, SH mean. This is my unknown. This is what I'm solving for. And then I have this 0.43, 0.43, and the right side is basically 3.12. I rearrange, I divide by SV. Well, when I divide by SV, PP is going to become 0.43, right? And then this becomes this. And this is what is basically here. Okay, so I have this 0. Either 56 or 62, I don't remember right now. That would be, so we knocked down this line, okay? We knocked down this line. Okay, now, before I go, I really want to go to this line, but before that, I want to go to this line, okay? Because this one is very easy too. Is basically for reverse, I'm on the reverse faulting region now. I move from this to this, okay, up here. Okay, how much is the SH max? How high can the SH max go? It's basically this line here, 2.187. It's 2.217. I remember because when I learned how to draw the polygon, I had to learn by myself in a cafe in Austin called Dolce Vita, which no longer exists. There was a very good-looking lady working there. Her name was Sam. I was calling her Samantha. She was taller than me, but it was 2017, and that's how I remember. It was yeah, it's a fixed value, 2.2017 for the conditions that we are talking about. And yeah, that's straight line, right? No big deal. Straight line, right? On the reverse faulting. Okay. What I was gonna say, I forgot. Okay, so now, okay, on my plot, I have this line and I have this line. So I knocked down 2 lines. I have 4 more to go. Okay, and now I'm gonna start using the second equation, which is the one that you have here. Let's go again back to the normal faulting region. Sorry. Normal faulting region. I will try to draw this line, okay? Now, I know the value of SH mean, the limiting value of SH mean. Is that 0.56 or 62 that I already calculated using this equation? So now that I know the SH mean, I basically know S3. And I need to plug it here. And then what is S1? S1 is 1, right? 1 psi per foot. And what is S2? It's SH max. So I now have only one unknown, because what is on the Y, what is on the x-axis, it will vary. So I solve for S2 in terms of alpha phi. So I make alpha phi vary from 0 to 3, and I solve for S2 being the unknown here, and will be constant, and it would be equal to 0 because it's normal faulting, right? So it will only stay within this region. Okay, so now I get my third line. Great. Now that I have 3 lines, how about I go to any questions, by the way? Any questions? All good? Okay. Now I will do this. This will be my 4th line. Okay. Again, I use this equation, the first equation, to basically find this. It's the same as the polygon. Okay, so now I know this is 2.217. And what am I doing now? I know this from this equation, so I cannot use this again. I need to use this equation at the bottom one. Okay, so it's a reverse faulting. So S1 is my unknown, my SH max. Sorry, I apologize. S1 is the known value. Is that 2.2017, okay? S3 for reverse faulting is the one, which is SV, right? Okay. What is S2 is SH mean, which is my unknown, okay? So I rearrange this to solve for an equation for SH mean as a function of alpha phi, okay? And in this case will be 2, because it's reverse faulting. Remember, n is 0 for normal, 1 for strike slip, 2 for reverse. And now I have an equation that gives me SH mean from alpha phi. And I ask Excel, okay, give or MATLAB or Python, give me SH mean for alpha phi moving from 0 to 3. And give me basically the variation of that. And then when I plot it, I get this value. Okay. I get this value. So now I have 4 lines. Those are the easy ones.
Linear one.
Huh?
Linear.
Yeah, pretty easy, pretty linear, pretty easy. Yeah. Now, the other 2, yeah. Now it's gonna be hard, okay?
The parabolic one.
Yeah, they are both changing quite abruptly. I don't know any of them. I'm talking basically about these 2 lines for strike slip faulting. Okay. Now I need the problem is that for strike slip, S1 is SH max, and S3 is SH mean. Okay, so I have 2 unknowns on the first equation, and I have what is S2? It's SV, which is known is basically 1, but this is an unknown. It's SH mean, which I don't know, and this is SH max, which I also don't know. So I'm a little bit with my back against the wall. I want to vary alpha phi to get SH max and SH mean, but I have 2 unknowns on the first equation and 2 unknowns on the second equation, right? So I basically have 2 equations and 2 unknowns. So I do simultaneous equations. And there are several ways you can solve these, whatever way you prefer, but you basically use 2 equations to derive 2 equations for 2 unknowns, SH max and SH mean. And the best way to do it, and this is how I do it, I use this equation to get me the expression for SH mean or SH max, and I plug it on the second equation, and then I ask it, okay, vary alpha phi from 1 to 2. No, yeah, when I was saying vary alpha phi from 0 to 3, that was wrong. You vary alpha phi for the range that you are looking at, 0 to 1 for normal faulting, 1 to 2, and 2 to 3 for reverse. Now it's gonna vary from 1 to 2, right? Okay. And this is how you get the remainder 2. And then you have the whole plot. And I make the coloring the way that with the color scheme that we have been using so far. What I was gonna say? Yeah, it looks like this. It's basically the limits. The way to understand, I think, if you have stability from this plot or not, is to go to the specific point. What Lunster was doing that he showed us in classes, in the lecture that he did for ARMA, is that he said, okay, backend, for instance, is something close here, right? So this is backend. You draw a line for backend like this. Okay. So I know alpha phi, but to understand if I'm stable under the conditions that I am, I need to have some extra steps, which sort of, it makes this more complicated than the polygon, but I still like it, and I think we can use it, at least at research level. And basically we can say, okay, for this alpha phi here, what is my SH max? What is my actual SH max? If the SH max is somewhere here, I'm above the limit, right? I'm above the limit. I will have slippage. Or what is my SH mean? Okay, it's basically because basically this plot is for those two lines. The limit for SH max and SH mean. And if I violate those limits, it means I'm violating this equation. And I have failure. So that's the plot of Lundstern and Zoback, I guess, for the limits of the horizontal stresses. Any questions?
No, I was thinking if we can get rid of, like, check the stresses,
Yeah.
like in the equation, we can change, we subdivide everything by SV. And it won't change any outputs.
Yeah, you do that,
Yeah.
right? You do that because what you plot on the y-axis is divided by SV.
I mean, even in the equation, if we take only one side and divide everything by SV, it won't change.
But we do it at a later stage, right? Just like we did with the polygon.
Yeah, but if we do it now, it won't change anything because it's like you multiply a number in the numerator and denominator.
Yeah, yeah, that's true.
So you don't need to multiply in the other side. It doesn't change the other side.
Yeah, it doesn't change the
Yeah,
other
the
side.
same thing for the parentheses S2, S3, S1, S3.
Yeah, you
Gonna be
divide by,
multiply and divide by SV. So
okay,
it's gonna be S2 over SV minus S3 over SV
yeah.
over S1 over SV minus S3 over.
So we sort of already do that. The problem is that, the good thing is that when you divide by SV, if one of them is SV becomes 1,
Yeah,
and then what is PP becomes 0.433, so automatically you get constants, you get variables turning into constant. And are you sick?
no?
Oh, you look a little bit sick.
No, I'm tired.
Yeah, I was tired this morning when I woke up. I was half an hour late for the meeting. Anyway, but I let him know. Yeah, this is, as Hakim said, yeah, it becomes easier, it becomes simpler.
Yeah, but as you said, like, it's not like S2 won't go with SV. It depends on what regime.
Yeah, where you are.
Yeah.
And if you remember Lunster in the meeting, he said it's a different equation for each line.
Yeah.
I think that's what he meant, like, it's, you have 6 lines. You need 6 equations, I guess, to get those lines. And the last one, because it took me over a week, slowly trying to replicate the plot. That was like 3 weeks ago or something. And then I had to color it a certain way, but to make it different than him for our paper. But it was the strike slip faulting. It took me so long to figure out, and I was like, oh, we have 2 equations, 2 unknowns. It's simultaneous equations, just like solve them together.
Yeah. I'm just wondering, you see in the polygon, we have one point in the middle of the diagonal
Yeah,
that has all the regimes together.
1, yeah.
What's that point in this graph? Is it the
Yeah.
bottom line?
No, it's those 2 points, I guess. At one.
No, it's all the regimes, all the colors. It's all a feed. So it should be all the whole
You're talking about basically this point,
Yeah,
this one. Oh, 1, 1, come
yeah.
on, the 1, 1, this,
The 1, 1, yes.
okay. The 1, 1,
It's not 1, 1, it's different here. They are in 2 points, separate. points.
yeah, might be,
No, it's not separate point, it's the whole bottom line.
it's not this and this,
That's what I was thinking.
But yeah, it's,
maybe,
yeah, but it's the whole line.
yeah.
It should be the whole line.
Did I color it wrongly?
No.
Could be.
No, it's just like, in this dimension, the
Yeah,
line becomes a segment. The
Yeah.
point becomes a segment.
Yeah, the
became a
point
segment.
become, yeah.
Yeah,
I guess so,
because
yeah.
it has all the colors.
Because you don't have 2 stresses, you have a fee.
Yeah, it's not the 2 stresses, yeah. Yeah. I guess so. Yeah. Oh, sorry. That about this plot. Yeah, it took a long time to figure it out.
I saw you drawing that with MATLAB, right?
Yeah, this is MATLAB. But I did it first in Excel. I wanted all the numbers in front of me.
Okay.
Yeah, it took me a while. But I remember Luster saying, remember, it's a different equation in every line. Right?
But the polygon is very short, better.
Yeah, the polygon has higher utility, I agree. I
The
agree.
thing is, if you have a no stress, you have like the 3 stresses known, it's
Yeah.
1 point, right? But here, you don't get 1 point, you get a segment.
Yeah,
If you're trying to relate SH to SH max and they belong to the same axis, they belong to the same axis.
yeah.
It's impossible to call it as a point.
Yeah, I don't remember what he used it for in his talk.
Exactly, like, for what? I'm thinking, how you can use this? What's the
I'm thinking if we can do the SH max SV as the axis. That will make a,
It would be better.
I
It
mean,
would be very better.
it would be, this line is basically SH max over SV the axis. And for this line, it's SH min over
If
SV.
it can be a 3D, it's gonna be different.
Oh,
yeah, but
yeah, perhaps, yeah.
And you will have the variation of AAP.
But the whole point is that you are trying to show 3 stresses on a 2D plot, right?
Yeah.
That's why you have the polygon. Otherwise, you do what
If,
the Australians are doing. What's the name? The Australian, the guy who won the paper contest in 2018, who had a 3D plot and basically had SH max as his V.
yeah.
Yeah, he didn't know that you could do this basically.
so if we have the stresses, should we calculate the A alpha first? And
If you
then
have what? Sorry? Sorry.
we have 3 stresses known.
Yeah, you automatically get the alpha phi.
So we do get the alpha P and then, but we have 2 points on the y-axis.
Yeah, you have two. So you have to use the equations that you have in place to find the limits of SH max and SH min.
Which would be the bottom of the circle that we have for.
Yeah, but
Right.
it depends on what this alpha phi is. Is it normal faulting? Is it strike slip faulting? Because for normal faulting, you have SV here, which is constant, and then SH min here. For reverse faulting, you have SH max here, which is variable, and SV, which is constant. But for strike slip, you cannot because you have one equation, 2 unknowns, so you need to combine it with something else. Strike slip is, I guess, the worst, from my understanding, the hardest to deal with. Even with the polygon, strike slip is the hardest because you have the line with the slope. But the rest
Yeah,
are
it
fairly
is
easy.
the hardest, but it's the one that make more sense. If we speak in terms of the more circle,
Yeah,
because in strike slip it's SH max maximum and SH min minimum as we
Yeah.
mean. So your S1 and S3 are SH max SH min and both are on the axis.
yeah,
However, if we talk about the normal faulting or reverse faulting, one of them is SV,
yeah,
and here we don't have SV over SV on the axis.
yeah. Yeah,
So
which is,
when we plot, we don't have to plot the
that's why the line is in the middle. Yeah, it's not either on top or the bottom. It's in the middle. Yeah. Yeah, I mean, it has to do with the regime. Has to do with the regime. Yeah. And I mean, he didn't do it for pore pressure, for pore elasticity, but pore elasticity multiplies PP. It's very easy.
Oh, yeah.
It's very easy to incorporate that into your equation.
So if we do let's say, if we take the same S1 and S3 of more circle and put it in the middle,
Yeah.
it will be 1 second.
If you take S3 of more circle and S1,
Yes,
okay.
S1 and S3, yes, in the more circle.
Yeah.
And then we put here, it will be a segment, right? One is SH mean, one is SH max with a known AP.
Yeah, but for that to be the case, you have to be strike slip, right? Because S1,
Yeah,
more circle only cares about S1 and S3.
yeah.
So if you have H max and H min as those, that means automatically you are in the strike slip for thing.
Yeah, but in terms of normal thing, one of them for sure will be 1.
Yes, which makes
Because
it
this is SV
easier.
over SV.
Yeah. Yeah, it's cost.
Yeah,
Yeah. Unless, I bet if you make this line change, it's gonna make the plot ridiculous. Anyway. So I will spend the weekend trying to fix homework 3 and give it to you guys on Monday. I have about half of it done. The thing is, I have a deadline on Monday, and now Monday is the 28th,
Yes.
and I also have a deadline on Halloween now because they sent us the SPJ proofs. I forwarded them to you. It was right after our meeting, and they give us 5 business days. That means
so
Halloween.
we have to read all of it.
Yeah, basically we need to make everything.
It will be really Halloween.
Yeah.
It will be scary.
Yeah, it would be. And then I have something on the 1st of November is the deadline for the homework of the other class. But I'm done with that.
Oh, we put scary post for naked.
No, it will be take a few days until it gets like posted or
I
something.
will put the SPE with spider.
But yeah, we have I will spend this weekend trying to finish the homework 3, make sure there is no mistake. Because when I give a new homework, there is always mistake. And when I make new slides, I'm surprised I didn't make a mistake on this slide. Yes. But yeah, if there is a mistake, we're gonna figure it later. And then we will proceed next week. I mean, we are good with the material. We are moving fairly fast. I don't want to move too fast. So we're gonna carry on with shear failure. And after that, we will look at some other stuff. Basically, what did we do? First module, we looked at the boundary conditions. Yeah, REV. Second module, we looked at the relationship between stress and deformation. Now we look at failure. We looked at tensile failure, and now we're looking at shear failure. After that, we are gonna put a web in it and see how does that affect everything. Yeah, Q stuff. And after that, we are gonna start looking at wellbore stability and stuff. So it becomes more of the petroleum side of things. Yeah. They told me that from next year, we may have some geology students in this class. Because there is no point in having geomechanics class in geology and geomechanics class in
It's very
petroleum.
important in geology.
Yeah. Fault slope
Yeah.
and stuff. So we might have some of those stuff here, more interesting. But I'm wondering, I think it's gonna be harder for the geologists to be in this class than the petroleum engineers to be in this class because of the math. Like the matrix stuff and the linear algebra stuff from module 2. I think it's gonna be a little bit harder I know they tried that in Texas and it was very bad. They tried that during my year when I was graduating. Then we had some girls from geology in our class, and they were like fairly. It was hard for them. Yeah, it was hard. It was hard for me. And I was like, it was my last semester. Yeah. So imagine how bad it was for them. I mean, anyway, we'll figure that out. That won't be a problem. Might not even be mine either. Anyway, thank you very much. Have a nice weekend. I will see you all on Monday. Don't drink and drive. Don't text and drive. Tip your bartenders.
Yeah.
Anyway, yeah, have a nice. Thank you.